Cabrera. He's going to talk about covariant description of colloidal dynamics. Cesar, go ahead.
Thank you. So, good morning. Firstly, I want to tell why we need a covariant description of the colloidal dynamics. There exists experience from theoretical approach, from experimentals, and from simulations that the geometry of the host medium for the colloid particles affects the dynamical and static properties. For example, if we measure the mean square displacement in a manifold with positive curvature, we have a subdiffusive MSD. On the other hand, for negative curvature, we have superdiffusion. The red line here is the Euclidean space with curvature 0. Also, if we consider that the manifold is a finite space, so they have an influence on the distribution of the particles. Also, we can identify some different time regimes for the mean square displacement. And here, the regions with higher curvature, here and here, have the greater probability distribution of the particles. Also, in experimental approaches, they measure the topological defects on the phase transition in an interface with colloidal particles. And here, we see the lateral diffusion of the protein in a cell membrane, but in the description, they have a flat space. So the curvature isn't present in some approach for the dynamical properties. So how we construct a covariant theory for the diffusion? First of all, we define a kind of geometrical confinement as an holonomical constraint. So with this constraint in mind, we can formulate the Langevin equation for the system. So the Langevin equation is in fact an stochastic equation. So we can apply stochastic calculus to obtain a diffusion-like equation. And finally, using some geometrical identities, we can obtain a covariant form of the Smoluchowski equation. And how this equation looks? Well, firstly, let's introduce some geometrical considerations. First, we consider that the particle lies in a manifold M, that it's a map from a space of dimension R, in this case it is R2, to R3. So the manifold lies in a higher dimension space. The map is defined by a set of local coordinates named x alpha. And with the local coordinates, we can define the tangent space to the manifold. Okay. The tangent space of the manifold as the partial derivative of the map. Also, in the tangent space, we can define the metric tensor. And here we have an example of the use of the metric tensor specifically, but for the line element. An important fact is that the colloids lies on the manifold, but the interaction of the colloids lies in the Euclidean space. So we have a kind of non-locality because they depend of the extrinsic distance, not only in the difference of the local coordinates. This is an important thing that we will see in more in detail after in the talk. Well, here we have in the left the Euclidean version of the equation for the diffusion, and in the right the covariant version. First, we work on the overdamped limit, so we consider that the time derivative of the momenta is 0. And so the change of the position is given by the white noise for the solvent of the colloids and the interactions. Here we have an operator that is the tangent vector. And also we can describe the system via the Smoluchowski equation for the joint probability of the system. Here we have, well, the derivatives, the Laplacian, and the gradient. So on the other hand, we have the Laplace-Beltrami operator and the covariant derivative. Now let's see in more detail that's the meaning of this. In the case of the Langevin equation, we introduce the tangent vector as a projection operator. We take the contribution of the first and project this over the manifold. So by the geometry, we need to introduce a new operator for the Langevin equation. In the case of the Smoluchowski equation, we have the Laplace-Beltrami operator and the covariant derivative. But the Laplace-Beltrami operator acting on a vector field, well, the covariant derivative acting on a vector field and the Laplace-Beltrami equations have the metric tensor. So the geometry of the manifold is contained in the differential operators. In the Euclidean case, well, we have the Laplacian and the Nabla operator without change. So what can we do with this? See, if we consider the Langevin equation, so we can implement Brownian dynamic simulation via the Ermac-McHammond algorithm. Here we present a study when we consider colloidal particles, paramagnetic colloids in a circle. Here we see how the interaction lies in the Euclidean space. The colloids move in a one-dimensional space, that is the circle, but the interaction lies in R2. Here we have the mean square displacement and the pair correlation function, firstly reported by Villada, Balbuena, and collaborators at 2021, and we resumed the study calculating the self part of the Backhand function. And also, we are currently studying systems with different interaction in confined to a circle. In this case, it's the mean square displacement for the square shoulder potential. Here we find a second plateau. So we think that it could be a kind of phase transition due to the finite size of the circle. Also, on the other hand, with the Smoluchowski equation, we calculate an approximate solution that allows to estimate some quantities, for example, the mean square displacement. Here, the first term is diffusion in the Euclidean space with a curvature. Now, here, this term depends only on the geometry of the manifold. Here we don't have interaction, so the geometry by itself introduce a different development for the mean square. Here we have the projection of the forces over the tangent space, but due to the non-locality of the potential, also we have the normal vector to the surface and the main curvature. So we have local and non-local properties for the mean square displacement. And here we have the definition of this term that relates the derivative of the vector of the tangent space. In another approach, also with the Smoluchowski equations, we define the reduced probability distribution over the space and introduce that the force can be derived by a potential. In this case, the potential is symmetric under the change of index, but here we see depends on the mapping functions, not only in the difference of the local coordinates. So taking this in account and defining that the correlation of the probability of two particles is contained in the Van-Hoff function of the curved space, we can integrate over the degrees of freedom of the particles of the system to obtain the Smoluchowski equations for the one-body probability distribution. Here we see an entropic contribution. If we don't consider interaction, we have diffusion due only for the entropy of the system. And also, we have a term that depends on the potential, so we identify this as the energetic contribution. Here, a difference with the Euclidean space, the limit does not go to zero in all cases because the finite size, for example, in this case, are only 5 colloids. So the ratio between n-1 and n is different can be very different to 1. And furthermore than the energetic and entropic contributions, we have the we have the geometry included on the covariant derivative in the Laplace-Beltrami operator, but also in the integral operator. Here, the square root of the determinant of the metric take the role of the Laplacian, of the Jacobian for this space. In summary, what we have, we implement Brownian dynamic simulation. Of course, in this case, I present the case of the circle. Also, we emphasize the role of the geometrical of the geometry in the diffusion. Here, for the mean square displacement in the solution for short times, we have the 3 terms that corresponds with the geometry. And also in the case of the Langevin equation, we introduce a new operator. Also, we obtain a covariant version for the Smoluchowski equation for one-body probability distribution. And why we're interested in this equation? Well, if we find a solution by numerical or analytical approach, we about to perform the Brownian dynamic simulation. So the solution of this equation, once we find how to solve, it's going to be faster than the Brownian dynamic simulation. Actually, currently we are working in the study of single file diffusion via the Smoluchowski equation. This is Smoluchowski equation. Also, we are working in Brownian dynamics in closed curves, like an ellipse. And we are trying to implement Brownian dynamics on surfaces. We are actually working in an sphere in an ellipsoid. Finally, I want to acknowledge to my PhD advisors, the Professor Castañeda Priego and Castro Villarreal, my friends and colleagues of the soft matter groups of the University of Guanajuato, and my student, Carlos León. And also, thank you for your attention.
Very nice talk. I had a couple of questions. First of all, you mentioned that, you studied your system with a shoulder potential with a number of particles that was relatively small, and you suggested that there could be some sort of a transition due to finite size effect, but this in principle you can check it. Cannot you? You could study systematically larger and larger systems to see whether you have a finite size effect in the shoulder potential results.
Yeah, this is a preliminary results.
Yeah.
It starts as a class project from Carlos, but we can see this. We want to see more. We increase the size of the system. and the concentration. And we find this, I forgot the word, comportamiento en inglés.
Behavior.
Behavior.
Yeah.
This behavior in systems with a greater size.
Okay. Okay, thank you. Can I ask another quick question? So, experiments by Lucho Isa's group at ETH show that there are colloids that, depending on they can change their diffusion locally. So you have, imagine a two-dimensional, it's like a chessboard where the colloid, depending on whether it's on a white spot or black spot, changes its diffusion. So my question is, could you extend your formalism to a colloidal system where diffusion varies locally? So it's not the same everywhere, but it sort of depends on where the colloid is.
Yes, is one of the things that they are working to do in the future, but the equations have some locality because we need to evaluate the geometrical terms in the position of the particle. This is the mean square displacement for a tagged particle. So we need the information that the position of the particle of the manifold to evaluate this expression. So here we have some locality for the development.
Okay. Thank you very much. Thank you.
More questions? If not, let's thank everybody. Okay, our next speaker is Karen Flores, and she's going to talk about mesoscopic modeling of enveloped viruses in fluids. Thank you, Karen.
Thank you. Good morning, everyone. My name is Karen, and I am a PhD student. Now, I will present our work, mesoscopic modeling of environmental viruses in fluid. So, many complex systems can be understood from microscopic interactions to macroscopic continuum descriptions. So, at microscopic scale, we can compute the movement of individual particles, for example, of atoms or molecules, where these atoms move according to Hamilton equations. And sorry. And this scale, the continuum theory, is a cross-grain versions of the microscopic scale. So in this scale, we can observe different continuum properties, such as temperature, density, and others. So interesting phenomena occurred at left scale between microscale and macroscale. This is the mesoscopic scale where systems such as these viral suspensions or lipids or gels can be described, and so different numerical methods have been proposed to simulate these systems. For example, lattice-Boltzmann, or multi-particle collision dynamics, or dissipative particle dynamics. Okay, the last numerical method is the one we use in this work, called DPD. So in this mesoscopic method, okay, retain some chemical properties by use cross-grain discretion, where the groups of atoms, okay, are treated as a unit, and these systems, all DPD particles interact through three forces, and the first force, conservative force, is as of repulsion, acting along the center of the particles, and this dissipative force is a drag force, act between a pair of particles, and finally the random force introduce the thermal fluctuations into the systems. So these wave functions and these amplitudes must satisfy thermal dissipation theorem. This is because DPD method has statistical mechanics corresponding to canonical example. Okay, with this method, we can study dynamic properties of complex systems, for example, virus suspensions. Well, in these suspensions, the diffusivity of virus depends on the following factors: structure details, and its environment, it's with suspended. So with this method, with this technique, we can explore these factors. So we propose a DPD model between two parallel walls, where the fluid particles' positions are random and their velocities follow a Gaussian distribution. On the other hand, walls particles are initially frozen at random positions, okay? And these walls are waterproof and hydrophilic. So finally, for the virus model, a rigid body is proposed, where each DPD particles represents a protein and lipids segment. Okay, in this illustration, we have a model of inviolate viruses that is virus with peplomers, and in this world, the number of these peplomers is systematically changed. So now we focus on understanding how virus responds to these amplitudes of oscillatory shear. Okay, therefore, this virus is introduced into the simulation box, and when the simulation starts, the walls move according according to amplitude of the oscillatory shear. So the top wall moving at a positive velocity, and bottom wall moving at a negative velocity. And finally, the fluid resistance to oscillatory shear, okay, is quantitative by the Pecklet number. Okay, how do we characterize these systems? Okay, first, um, to characterize the hydrodynamic field, the y-axis is divided into slabs where the mean velocity of fluid particles within each slabs is calculated to obtain a velocity profile. So, then to characterize the dynamic of the virus, we obtain the rotational diffusion coefficient. So, from the expression, okay, for the angular momentum, we can obtain the rotational velocity, and this in these components of this velocity, we can calculate the mean square angular displacement. And finally, we obtain the rotational diffusion coefficient at long times. Well, we first study the response of this fluid under oscillatory shear. Okay, in the first figure, we can say for low Peclet's numbers, the fluctuations contributions plays an important role because because it dominates over oscillatory shear flows. Okay, but for Peclet's numbers greater than 1 in figure B and C, the computation of the thermal contribution and the oscillatory shear effects becomes evident. Okay, so we can say as Peclet number increase, the thermal contribution decrease. So, and finally, we also study the behavior of the fluid at Peclet numbers much longer than 1, where the oscillatory shear effects dominates over the random contributions. As results, we obtain different regimes. Okay, well, we aim to understand the virus response to these different regions. Okay, so in the first figure, we observe that rotational diffusion coefficients tends to decrease as the number of peplomers. This rotational diffusion decrease when the number of peplomers increase only for high Peclet numbers. Okay, and in this behavior is shown in this figure. Okay, unlike for low Peclet numbers, we observe that the rotational diffusion doesn't change when the number of peplomers increase. So this rotational diffusion of the virus is also affected by the behavior of the fluid, where this rotational diffusion increase exponentially with Peclet numbers. Okay, so for high Peclet numbers, okay, our results report the same behavior of this works only for high Peclet numbers, okay, and this method allows us to explore the importance of these thermal fluctuations in a fluid, in a DPT fluid, to subject oscillatory shear. this is, allows us to study the dynamic of virus um, to, to, to different environments, to different regions. Okay, so in this world, we also study the case of the cuvette flow and Poiseuille flow, where for high Peclet numbers, we obtain laminar flows, and for low Peclet numbers, the thermal fluctuations dominates. Okay. In conclusion, the rotational diffusion of the virus depends on the number of peplomers, only for high Peclet numbers, and the relationship between the rotational diffusion and Peclet numbers is exponential for all virus models, that is with or without peplomers. Okay, so in this work, okay, the virus response can be associated with successful infection and virus rheological properties. Okay, this is all. Thank you very much for your attention.
Thank you, Karen. Questions? I have a question.
Yeah.
Is there interest in looking into the translational diffusion? You have focused on rotational diffusion.
Yes, only rotation. But this previous work, Moreno 2022, studied the translation of the virus. But in this world, only study the rotation of the virus.
Okay. More questions?
Me. Hi, Karen. Thank you. Do you think that the rotation of the particle can change how it will bind to a cell membrane, for instance, and therefore increase the likelihood of a proper binding between the particle and the cell?
Okay. So, depending, yes, but in this rotational diffusion depends on the number of peplomers and the behavior of the fluid. It's only is all results in this work. No, it's only this. Maybe as perspective, we can explore other properties of this rotational diffusion of a virus with peplomers. Okay.
Okay, let's thank Karen again. Okay, our next speaker is Jorge Escobar Agudelo, and he's going to talk about generalized effect medium theory for elastic systems with correlated disorder. Thank you, Jorge.
Thank you so much, and thank you all for being here listening. This is the presentation I did for my master's dissertation in the IFT UNESP. And first, I want to acknowledge my advisor, Professor Daniel Liarte, and also a postdoctoral student, Hui Aquino, and FAPESP, which fellowship allows the development of this project. The first thing I want to do is to give a context about the title in general. So we are working with disordered materials. We know that in solid-state physics, we can describe the structures of solids using these crystalline solid periodic structures. But in nature, there are also materials that doesn't have this periodicity. They are disordered systems, and we call them amorphous solids. Inside this family, there are also systems that have correlated disorder that, for instance, are colloidal gels that have attractive interactions. So we can read this as if we have a colloid in a side, it will increase the probability of having colloids in the surrounding. And this correlated behavior is very important because it shapes the structure of the amorphous solid in particular. So what happened is that when we try to study rigidity or elastic properties of this system, we usually use rigidity criteria. Like for instance, the Maxwell criteria tell us that the coordination number, that is the contents per particle on average, must be at least 2 times the dimension of the system in order to our system to be rigid. But we want to if we want to study this order system, we need to use effective medium theory. What happens is that this effective medium theory doesn't include a system with correlation disorder. So what we wanted to do is to introduce this generalized effective medium theory in order to build this bridge and be able to describe elastic systems with correlated disorder. Basically, the first thing we use is rigidity percolation. That is basically, if we have this lattice here, we'll have a coordination number, that is the average of links. And if the coordination number is greater than this Maxwell criteria, our elastic moduli will be greater than 0. If we start removing links in our lattice, we can see that the coordination number decreases, but also the rigidity moduli. So if we can keep doing this, so if we remove more, we will have this behavior until we reach a critical value of this coordination number. And at this point, we will have a rigidity transition, so our system is not rigid anymore. And if we keep removing more links, this will be 0. So we are interested in this critical value of rigidity transition, and we keep studying them in correlated systems using effective medium theory. So for the effective medium theory, we use coherent potential approximation that basically allows us to describe a lattice that would describe a system that is disordered. So we can map, using this coherent potential approximation, map this disordered system using a lattice that is homogeneous and has a defect. This defect has certain probability distribution. So the way we know that we can do this mapping is using the self-consistency constraint that basically tell us that a green function of this lattice, if we take the mean value over all of the possible defects, it must be exactly the green function of a homogeneous lattice. But if we use Dyson equation, this is basically saying that the mean value of the T matrix of our system must be equal to 0. So our challenge here is that we want to study correlated system, but if we look only for one defect, we cannot describe correlations in our system because this defect is independent of what is happening in the surrounding. So acknowledging that some systems have correlation between the disordered elements and the neighbors are important, our objective is to build an extension of this effective medium theory. I am not talking about the specific details of calculation, but the general idea is that we introduce more defects in our system. So our system is more general, so instead of looking just for one link, we are looking for more. And also, the probability distribution that we use to calculate this mean value is more general and includes the information of the correlations. So we just developed this coherent potential approximation for a general system. We conclude with this equation that we can talk about the details later. But the important thing here is that when we want to calculate this mean value, we can see that this mean value is taking over the possible defects. So these terms here are not important. So in this sum of over all of these terms, we only need to calculate this mean value here. But we will need that all of these mean value are equal to 0. So our general approach is to calculate a system where we define this new eighth matrix, which is each ij component has this form here. And we need to all of these equations be equal to 0. So we can test this using a simplified system, and we use a simple model with correlated disorder based in this idea of attractive interactions between colloidal gels. But the main idea is that basically we describe this as using as the homogeneous lattice the triangular one. And we use a probability protocol when we just start with a system that has no links. So the probability of having one link is just P, or not having link is just 1 minus P. But in order to introduce a new link, we need to acknowledge the correlation that exists. So we need to introduce this F, that is basically a module that will introduce these correlations effects in our probability. We then need to describe this F more particular for our system, we do later. And in terms of calculating the probability of adding a new link, we square this F in order to account for the double effect of these two links. For the other cases, here, if we have one link, we just need the effect of one of these F modulo that affects the probability. And for the cases when we don't have links, the probability is still be P 1 minus P. So we have 8 different probabilities here. But we can just impose that a configuration that only has 2 links have the same probability, also the same for the ones that have one link. And at the end, we finish with 4 possible probabilities. The probabilities of having 0 links, that we take this as a joint probability. It is just multiplying all of these probabilities in this path. And for the probability of having 3 links is just this path here. And for the other ones, is just to take the average of the configuration of having 1 link and having 2 links. It is very important to define this F as a function that respects the normalization criteria for the probabilities and actually accounts for the correlation in our system. So we use this arbitrary function that introduce a new parameter, that is the alpha parameter. This alpha parameter accounts for the correlations, and when alpha is equal to 0, we don't have correlations in our system, so F is equal to 1, and we have the same probabilities as if we don't have correlation. But as alpha increases, the effect of our correlation is greater. So we can use this just to describe probability distribution in our system, and we use the F matrix we described before, that is the idea we developed. So we can now calculate this F matrix. So our new cell consistency constraint basically is to set this equal to 0. And since P is a function of the parameter alpha and the probability parameter, and F is a matrix that depends of the elastic constant, we can describe the behavior of the elastic constant in terms of the parameter P for different values of alpha. So for alpha equals 0, when our system has not correlations, we can see that we have exactly the same behavior I introduced in rigidity percolation. We have this, the value of this constant that accounts for if our system is rigid or not, reach this 0 value of as this critical point, that is 2/3, and I have this linear behavior until I reach the value of 1. So my system is rigid since this point here. And when I introduce alpha, I can see that I have a shift in this critical value of P. And that makes sense because since my system is correlated, then I reach rigidity for lower values of probability. Looking for this result, we can think that maybe our system reach rigidity for lower values of coordination number. So if we study the behavior of our system in terms of coordination number, calculating coordination number using the probabilities I defined in the probability distribution, we can see that independent on the correlations, we have the rigidity transition exactly at the same value that respects the Maxwell rigidity criteria, that it's 2 times the dimension. In our case, it's 4. And 6, that is the higher value for a triangular lattice. So we don't have shifts in the rigidity and the coordination number, and maybe we can think, looking for this, that correlations doesn't affect the correlation number, but that's not true, because if we describe the coordination number using the protocol we described before, we can see that the coordination number is a function of the parameter alpha, so correlations affect the coordination number. But if we calculate using this, because this is an analytical approach, we are able to describe explicitly the form of K and the form of Z. If we do the description of the elastic constant in terms of the coordination number, we can see that the factorization gives us exactly this behavior. So we don't have an explicit dependence of alpha of the elastic constant in terms of the coordination number. We have this behavior, but correlations does affect the coordination number and the elastic constant. So we can also do some scaling variance. So we just use the fitting parameter phi equal minus 0.15 for different values of alpha for this delta p, that is the shift in the critical value of the p parameter. And we can see that for this fitting parameter, all of the plots collapse to the same behavior. So we have scaling variance and we have universal behavior in our generalized effective medium theory. So for the conclusions, we extend the CPA through a flexible framework capable of describing systems with more complex probability distribution, allowing incorporation of spatial correlations into rigidity analysis. But also we can see that we include this correlation in the calculation of the mean value. So actually we have a system that allows us to apply this effective medium theory for more general structures. And correlation shift the critical parameter PC, but the rigidity transition aligns with Maxwell criterion. These also are shown in last works that we can see that we have this shift in the volume fraction when we introduce correlations in systems as colloidal gels. So what we want to do in the perspectives is to explore new systems without translational symmetry or more complex interactions, because the model we described here was very simple, but also contrasting our results with the study showing shifts in volume fractions, just using last results, using our system to study this other kind of system and see if we actually have these shifts in these parameters. Actually, we are doing this using our method here, and we can see that we have the shifts in volume fraction, but we don't have shifts in coordination numbers, so it is basically in agree with the results we have here. So thank you so much.
Thank you very much. Beautiful talk and beautiful work. I was wondering about the dimensionality of the system. So here you assume the two-dimensional system, I think. Is your theory easily generalizable to arbitrary dimensions? Or?
I couldn't see why not. Just.
Yeah, me neither. But maybe
yes,
we're overlooking something.
Usually, when you use this effective medium theory, introducing a dimension, the most results is that there is not a difference in dimension.
Can I ask one additional question? On alpha, if you would let it tend to infinity, do you?
That's a great question. That's ideally what we wanted to do, just an alpha that it's infinitely, that could grow infinitely. But when we introduce this in the behavior of the function, that this is an arbitrary function, we can see that we have problems in the definition of probabilities for alpha greater than 6. So we didn't include this value, this specific value, but this is just a problem of the simple model we describe. If you describe, because this is, if you want to describe a system with a specific behavior that you can describe the correlations and how this affect probability and you know how to do it, you can use this model in order to describe this system. Just for our simple model, alpha cannot grow infinitely, but you can describe other kind of functions.
More questions? Okay, Chantal.
Thank you very much. Very beautiful talk. Just two quick questions. One, can you test your model against, because there are many different systems that can form colloidal gels. You can have physical gels, chemical gels, you name it. So with very different interactions. Could you actually test your theory against
Yes.
experiments?
That's a good question because the idea of describing colloidal gels is just a motivation. So this is not a model for colloidal gels. This is a general model. So we use colloidal gels as a motivation in order to describe these attractive interactions as correlations. But basically, you can describe more general systems. So when we try to describe more general system using this new definition of the AIF matrix and calculating this mean value, you can see some details that the calculation could be very difficult. If your system is very complex, or if you have very complex interactions, it is not, in general, an easy calculation. So this is why we needed a very simplified model in order to test it. But you can describe very general system.
Can I ask you, sorry, the very last one? How difficult would it have been to build some sort of a Monte Carlo scheme where you break and form these interactions, you have probabilities, and basically, I mean, sounds to me a bit easier than building all the theory. Maybe, I don't know, a Gillespie scheme, sort of, where you break and form bonds.
Sorry, I didn't understand.
So a Monte Carlo scheme, where you break and form these connections.
Okay, maybe you can use more general way to describe this probability distribution. You can use Monte Carlo or other approach. We just develop the generalized system and use a very simplified test. But this is the good thing about this work is that now you have some furniture and then you can start building.
Yeah. Thank you very much.
Thank you.
Okay, let's thank Jorge again.
Thank you so much.
Yes.
Okay, our next speaker is Daniel Canavello.
Canavello?
Okay. Align active matter in periodic obstacle arrays.
Yes.
Thank you, Daniel.
Thank you. Yes. So, my name is Daniel. I'm going to present a work on aligning active matter in periodic obstacle arrays. So, this talk is divided into 4 parts. First, I'll introduce what is aligning active matter. Then I'll talk about the behavior of a system without any obstacles. Then introduce an isotropic obstacles and then make it an isotropic. So first part, it's an introduction, why study a system like this. So active matter, many people here probably know what it is. Usually has a heading vector, which it propels itself into. But the velocity is not always aligned, so it can be pushed somewhere else by external potential or other particles, and it creates a certain angle difference between the velocity and the heading. So it can be seen during a drift or a glide. For a bird can be flying in a direction, but moving to another. And it's seen that several systems have a sort of alignment that tries to bring these vectors together. So for example, bird flocks, tissue cells, or even V-check systems can have self-alignment instead of explicit alignment. And we couple the system with a periodic array and compared the results with regular active matter without the self-alignment in the system. So we started with this and tried to see what would happen. So if we don't have any obstacles, that is just an interacting system with active matter, we have these equations of motion, a velocity. It propels itself with a constant velocity along a heading vector, which is directed by theta, and an exclusion force, which we use a WC potential. That is basically a purely repulsive Lennard-Jones potential. It's very common as well. And the theta, the angular velocity, has a thermal noise, which is pretty standard, but we include a torque that tries to align the heading with with the force, which is basically the velocity, if you can put in there. And it's controlled by a parameter called beta that controls the strength of this torque. So the higher the beta is, the quicker this alignment between heading and the force will happen. This is kind of abstract, so this is the illustration of how this happens. This is 3 time instants. In the initial moment, we have the head and the velocity are aligned for both particles. They have a size and a certain interaction radius. When they come into contact, these forces will be perpendicular to their contact, so there will be a force. And the heading will be as before, but the velocity is different, so there is a certain angle between them. So the beta will create a torque that will try to bring the N together with V. After a certain time, they will once again be aligned, but the orientations will be different from the start. So despite this happening, being a self-alignment, happening only between each other, it can still make a system make 2 particles align together after a collision. Here we have 2 examples of a system. This is a system with very low beta. Everyone has a different alignment. The density is very low, so there is no MIPS or other phenomena like this. It's just random motion. But when we increase the value of beta, everyone is on the same direction. Here you can see it, they're moving downwards here. So we have a flocking motion, which is very understood as well for V-check systems as well. But this is with just the beta parameters. We found that the critical value of beta for this to happen scales linearly with d over n. We can see here a plot to scale it with n. We see that it collapses really well. So we have found a generalized, this also applies for several systems. Negative beta, with very beta, we can see when it will transition from paramagnetic motion to a flocking motion. This is the velocity of the system, which goes from 0 to 1. So if we introduce an array of obstacles, what would happen with the system? We initially model our obstacles as these black dots, which are just pinned particles. They have the same size and properties as regular particles, and see what happens. Initially, we try to see if it would change the critical value of beta. It doesn't change, it stays relatively the same. But the final velocity drops as the density increases because it has more collisions, and it can't reach a higher velocity as it did before, so it screens them out. And then we also see that for increasing a density, the movement of the particles, the tethers, starts being peaking around the 90-degree angles. So you can see here. For no pulse, it's kind of isotropic, but as you increase it, it only peaks around the symmetry directions of the potential. So it's only 90, 180, 270, which is kind of expected as well. So we try to make it anisotropic, which is we keep the number of obstacles in one direction constant, and only vary it on the x direction. So we can see that here we kept the number on x fixed, the number of obstacles on y fixed, and change it on x, so it starts isotropic at 8 by 8, and as we increase the number on x, the velocity on x increases and the velocity on y decreases. And we found that it happens, the system undergoes a laning transition, which is, here's 4 frames of a video. I couldn't put the video to work here. But basically it starts isotropic, the system, randomly generated. But as the system has a time evolution, the particles will try to align themselves into lanes. So there will be a dimensional transition. It will go from moving from 2 dimensionals to move only one dimensional. This is well above the value of beta for critical motion, for flocking. So we can see here that it forms a lanes that try to move only one direction, it's very dense, some empty lanes, and some lanes move into other directions. So it is moving here on the x direction. And we basically found 3 phases on the system. Here's a quasi-isotropic. It reaches from the up to about 15 posts, where it can still move vertically. But here, it can individual particles can move vertically between these posts, but they prefer to move into one direction. And finally, if we make them too tight, it basically has a dimensional reduction of the system, in which each lane becomes an isolated system. It can communicate with each other, so the density stays the same along the time, and the direction they pick, it's basically random, which is basically 50-50 in the direction they choose. And this was basically what we found. This was published on Soft Matter this year, yes. Professor, along with the Highcard couple and my advisor class, who couldn't attend. And we also have a work about this system where we confine it with a harmonic potential, but I couldn't fit it with the allotted time. But if anyone wants to ask about it, feel free to. And yes, that's basically it.
Thank you, Daniel. Questions?
Has any questions?
Thank you very much, Daniel.
Thank you, Pablo.
What do you think would be the effect of adhesion between the particles? Because it is well known that these self-aligning particles, they model well tissue cells.
Yes.
But in these models, usually they adhere irreversibly.
Yes, there are some systems I'm kind of working with right now with this kind of interaction, yes, adhesion. Let me see here. Here. Basically, what we saw quickly, what we saw is that basically it starts to clump more between when it flocks. Everyone has to find a very dense core and a very sparse outside. But we didn't explore much this part of the system.
How do you distinguish the 2 regimes in the phase diagram when you say couple lanes or uncoupled? Is this something?
Yes, we basically studied the interfaces and the density in each lane. Because as you can see here, we have, basically here we have, between each lane, we have basically a 50% chance if it moves to the left or to the right. And here it can be coupled, there's a higher chance of moving in the same direction.
But do you have some physical reason for the interactions to be more important in one case than in the other?
Basically because there, at this point, the spacing between obstacles in this direction is smaller than the particle size, so it can't jump between lanes, basically. So this transition becomes harder to see. We also have some parameters I didn't include here because they're very technical, but let me see where I put it. Here. There's these 2 lines, basically, which we consider transitions for the coupled lanes and the uncoupled lanes. But it's basically because the biggest reason is the spacing becomes too small for particles to go through.
Okay, thank you.
Thanks for the great talk. Do you consistently, so the coupled lanes image here, there's like highly heterogeneous density of the actual particles. Do you consistently see that the isotropic phase and the uncoupled lanes phases have a more homogeneous density, and then the
yes, the isotropic phase, it's very similar to the case without with the isotropic case. So basically, the system just flocks into one direction. It has not much heterogeneous density, basically because, like Pablo talked, there's no adhesion. So they basically just couple themselves into one direction and move there. In the uncoupled lanes, it's harder to have heterogeneous density because each lane is basically an isolated system. So the density for each part remains constant over time. So there is not much reason to have. All these heterogeneous density waves basically only happens here because particles can move upwards, but they prefer to move sideways. So they will just keep moving that way in very dense lanes. So basically,
Okay, let's thank Daniel again.
thank you.
You are the last speaker, right? I think so. We can triple check. Is it late?
I think so. I think we have to. He's coming. Vamos pronunciar esse último nome. Separdar?
Leila Separdar.
Leila Separdar. So our last speaker for this session is Leila Separdar from the Federal University of San Carlos. Leila, you can go ahead.
Good morning to all. I am Leila, and today I'm going to talk about the liquid crystal, a work that I have done on liquid crystals. Besides the work that I have done on crystallization that Professor Zanotto in his nice work addressed to it, I independently did some simulation on thermotropic liquid crystal, and this work has been done by molecular dynamics simulation, and the molecular model that you are seeing here is in this model the system composed of ellipsoidal particles, and I'm going to show you some results related to the effect of molecular aspect ratio, the elongation of this ellipsoidal particle on structure and dynamic of this molecular model. The liquid crystals are a state of matter that have properties between those of liquid and solid crystal, and they follow like a liquid, but can also have a degree of order similar to that of crystal phase. And there are some types of liquid crystal. In the isotropic mesophase, there is no translational and orientational ordering. In the nematic phase, molecules are oriented in the same direction, but there is no positional ordering in this mesophase. And in the smectic phase, molecules are organized into layers, adding more structure than nematic. There are different kind of nematic phases, such as smectic A and smectic B. The smectic B shows more positional order than smectic A. The liquid crystal, as you know, is very important in the technology, and especially in display technology, and not only in technology but also in food industry. The liquid crystal are used to stabilize dispersions and emulsion. And a lot of work have been done to study the complex behavior of liquid crystals by experiment, theoretically, and by computer simulation. However, in this work, we focus on the molecular dynamics simulation using a Gabern model to answer questions concerning the effect of aspect ratio on the liquid crystal properties. And the system that we have simulated composed of about 3,000 ellipsoidal particles at pressure 4, and the interaction potential between the molecules were defined by Gay-Bern potential. This Gay-Bern potential has a parameter that relates to the shape of molecules the shape of molecules are ellipsoidal, and the three other exponents related to the strength of the interaction between two molecules. And to find if there is any phase transition in this system, I forgot to explain it. Here we didn't change the strength of the interaction, but we changed the K, the size of the ellipsoids, and for And for 4 different aspect ratio, 2, 3, 4.4, and 5, we simulated the system, and to find if there is any phase transition, we started from an isotropic mesophase, and then we cooled down the system to reach to the solid phase, and then reheated it. As you can see, from this, the potential energy as a function of temperature, we conclude that for the lowest elongation, K equal 2, only one phase transition from the isotropic to crystalline phase occurs. However, by increasing the aspect ratio, and nematic and semectic mesophases were also induced. And for the largest aspect ratio, the nematic and semectic A stabilized over wider temperature range. After that, we looked at the orientational ordering in the system. In the isotropic phase, we calculated the order parameter from the order tensor, and the largest eigenvalue of the order tensor is order parameter. At the isotropic mesophase, the order parameter is 0 because there is no orientational ordering. However, by decreasing the temperature, at temperature that the transformation from isotropic to nematic phase or from isotropic to crystalline phase occurs, we can see a jump in the order parameter, which demonstrate that some orientational ordering is forming in the system. And to see how, from this tensor, we can also find the director vector, the direction that the molecules arrange themselves or orient in that direction. And to see what is the structure of these layers, this layering structure, and also the structure of a molecule in each layer, we calculated the translational pair correlation function for all systems at different temperatures. And as you can see, this function has a periodic behavior, and the period of each curve can indicate the interlayer spacing, and if by increasing the K, as you can see, the interlayering spacing, the distance between two peaks also increases. And by calculating the perpendicular radial distribution function, we can find out what is the structure of molecules in each layer. From the coordination number as a function of distance, the coordination number is area under the first and second peak of this function. We can see that for K equal to 2, only one plateau appears here around 6, which demonstrates that the system with aspect ratio of 2, the layers has a FCC structure. However, by increasing the aspect ratio, we can see a second plateau at value of 12 also appear. That this second plateau demonstrating that the system, the structure of system is changed, and it's changed from FCC to HCP because this coordination number is characteristic of hexagonal or HCP structure of each layer. We also calculated the diffusion coefficient parallel and perpendicular to the director vector to see how molecules, by changing the temperature, move inside the system. For system with K equal to 2, as you can see, the diffusion coefficient and its components are equal, which demonstrate that the diffusion coefficient has an isotropic-like behavior. However, by increasing the aspect ratio to 3 and 4.4, an anisotropy in the diffusion in the nematic phase can be seen. And as you can see, the diffusion coefficient parallel to the director become higher than the diffusion coefficient perpendicular to the director. And by increasing more the aspect ratio from 4.4 to 5, we can see that the diffusion coefficient in the parallel direction also increases, but the diffusion coefficient perpendicular to the director vector doesn't change significantly. So by increasing the aspect ratio, the decoupling was observed, and for all the mesophases, this decoupling was high along the parallel to the director vector was higher than the diffusion coefficient perpendicular to this director vector. And then in this figure, we plotted the maximum anisotropy seen in the diffusion as a function of aspect ratio. And we found that this point related to our simulation, and this dashed line related to the numerical solution of the hydrodynamic equation using a slip boundary condition. And as you can see, the result of our MD simulation is in agreement with the solution of this hydrodynamic equation with a slip boundary condition. We compare our result with the previous work done by MD simulation related to the motion of needle-like molecules in the sea of a sphere that are shown here by these stars. In that system also we can see that the maximum anisotropy of diffusion as a function of aspect ratio can described by the solution of hydrodynamic equation with a slip boundary condition. Here the square and triangle related to the result obtained from the experiment. So we can conclude that the ellipsoid with higher aspect ratio diffuses faster in the parallel direction with a higher ability to slide past each other when they are mutually aligned. So in the main result, to sum up my talk, the main result that we obtained was that for aspect ratio at pressure 2, 3, 4, and 5, at pressure 4, we saw that as K increased from 2 to 5, the nematic and smectic mesophases were induced and stabilized over wider temperature range, and also the structure of system by increasing the aspect ratio changes from FCC to complete HCP in the smectic B mesophase of K equal to 5, and a decoupling between parallel and perpendicular diffusion coefficient was observed for a K higher than 3, and in all mesophases, the diffusion coefficient parallel to director vector was larger than the value we obtained for perpendicular diffusion. And the result that we obtained was in good agreement in the result obtained from experiment on real thermotropic liquid crystal. And thank you for your attention.
Thank you, Leila. Questions for Leila? Dan.
Thanks. I was wondering if you'd tell us more why you expect or don't expect the hydrodynamic approach to give you the right answer here. For a colloidal liquid crystal in water, it makes total sense, but this is a molecular liquid crystal.
The solution of a hydrodynamic equation, because this hydrodynamic Navier-Stokes equation have been solved for with two different boundary conditions, S-slip and S-stick boundary condition. I didn't show here, but the S-stick boundary condition tell that by increasing the aspect ratio, this maximum anisotropy in the diffusion coefficient doesn't change. It's a straight line. But S-slip boundary condition shows that by increasing the aspect ratio, this anisotropy also increases. And can describe the result.
Thanks for this very nice talk. I mean, besides the diffusion, when we look to the liquid crystals, either experiments, etc., there are a huge number of experiments, either for thermotropic and also lyotropic. Do you think that you can extract from your simulation other parameters that you can compare with real experimental data?
With the real experimental data, we should simulate the real liquid crystal to tell anything about the behavior of that system. And simulating the real liquid crystal needs a good force field and also need a big simulation box and a big time scale for simulating it. But what we can only this molecular model can only give us some insight about the general behavior of liquid crystals. And I did this work I was thinking about how I can connect the crystallization, the classical nucleation theory, to this model molecule.
More questions? Okay, so let's thank Leila again.
Thank you so much.
We have lunch break now. There are a number of options around here. We will send some recommendations via the WhatsApp group that some of you might have signed up or registered. You might have